Welcome to this video on the topic of networks. In this video, we'll be having a look at how we can go about finding all of the paths between two nodes in a network. Now, all paths in a network can be deduced in a systematic and repeatable way. All sensible paths in a network may be easily found in a network where nodes are positioned such that movement upwards or to the right is considered as progress. Progress is in that you're moving closer towards your goal. So looking at this network over here, all of the nodes in this network are positioned such that if you move up or you move to the right, you're moving closer to your node B. So B itself has to be the furthest node away from A. Now the way in which we're going to find all of the paths within a network between two nodes is we've got a very simple algorithm we can use. So it consists of three rules in an unconstrained network. So rule 1 is you may only progress forwards. Forwards being defined as moving to the right or moving in an upward direction. So if we were at this node in here, we're unable to move to the left and we're unable to move in a downward direction. Reason being is that we're moving away from our goal, which would be node B. The second rule being that the first progression is assigned a path count of 1. So if you're starting at node A over here, as soon as you move forward in either this direction or this direction, the path count from A is always considered as 1. And then finally, subsequent progressions have a path count equal to the sum of the paths at prior nodes. Alright, so only 3 rules, but still a little bit confusing looking at it right now. So what we're going to do is we're going to do example 1, find all the paths from A to B. What I'll do is I'll guide you through the implementation of this algorithm over here to find all of the paths we have starting from A and finishing at B. Now to begin this, what I'm first going to do is I'm going to identify the node that I'm starting at. In this case, I'm starting at node A. From there, I'm going to deduce all the paths that I could potentially travel across in a forward direction or a direction that's indicative of progress. Now for that, I can either move upward in the direction of this arrow here, or I can move to the right in this direction here. Now, in accordance to our the second rule, the first progression is assigned a path count of 1. So what I'm going to write is at this node here and this node here, there is one path leading to this node. It's coming from A, and there's one path leading from this node, so also A. Now from there, we're going to go for our second progressions. So looking at this node here, we can either go up or we can go across like so. Now the progression from this node to this node is equal to 1. And the progression from this node to this node, well, it's equal to 1, but it's also going to be equal to the progression from this node over here. Noting that you can go from this node up to here, and this node, you'll arrive here from either this node or that node. So we have to do the progression from here to there first. Looking at rule number 3, subsequent progressions have a path count equal to the sum of all paths at prior nodes. So that means that the number of paths we have at this node over here is going to be equal to this node plus this node. So 1 plus 1, that's simply going to be 2. Now finishing off the other node. Now I'm going to repeat this algorithm for all of the nodes until I finally reach my destination B here. And finally finishing the pathfinding algorithm off. The total amount of paths we have that will take us from A up to B, we have 35 different paths. So all we do is we assign the first branches off the initial node as a path count of 1, so here and here. And then when we reach a node that can be reached by multiple nodes, you sum all of the path counts together. So in this case, from 1 and 1, we have 2 over here. You go up to 3, 3, 4, 6, 4, 10, 10, 5, 20, 15, and 35. So what you can see is that the complication here mostly comes from drawing all of the arrows and summing the numbers together. But overall, it's just 3 rules that we have to abide by. Alright, now that we're okay with being able to find all the paths between nodes or two nodes on a network, let's have a look at how we can do it when we have constraints. So consider example 2, we have find all paths from A to B while passing through C. So what this means is that progression itself is always going to require you to pass through C, and then from C you can go to B. Now for this particular node over here, or this particular example over here, we have to add one more rule to our rule table. Now the rule we're going to add is that the path count to all irrational nodes, or all nonsensible nodes, is automatically going to be assigned the value of 0. So when I say nonsensible or non-rational, what that means is that if we're at a node and it doesn't actually take us through, say for example, the node that we need to go through. So if we look at these nodes up here and up here, what we're going to find is that if we're at these nodes here and here, they won't allow us to get to C, and even if we did pass through C, they're not going to be intuitive to go to B because you'd have to go backwards. So instantly this node and this node are going to be removed from all possible path count. So what I'm going to do now is I'm just going to add that to our rule table. Alright, now starting this off, what I'll do is I'll draw in all of the arrows denoting pathways that are sensible. So you can see the nodes out here and here. It would not be sensible to visit them because if we did, we'd be moving backwards to go to B or to go to C. And similarly, the nodes here, here, and here, they're not sensible either because again, we'd have to be going backwards to go through C or to go upwards to B. So these guys themselves, they can be crossed out. So we're not going to visit them. Doesn't make any sense to. Okay, next step is all of the nodes that we're not going to visit, I'm going to assign them path counts of 0. And just to unclutter the diagram, I'll remove the crosses. So that just denotes that we're not going to travel along them. Now next step is we have to fill in the effective paths that we're going to use. So starting from A, there's one path to these two nodes, and there's one path here and here. So all the outliers have a single path. Now the next node we're interested in, the path count here is the sum of these two. This will be a 3. Also a 3. And the path count towards C, in our case, is going to be 6. So all nodes have to pass through C. From there, we're going to get a 6 up here and a 6 here. And then we're going to go 12 over here. Still 6 over here. And finally, the amount of paths that lead to B are going to be 18 unique paths. So in summary, to be able to solve this particular question here where you must pass through a particular node, what you need to do first is identify all of the pathways that lead to, or all of the nonsensible pathways that would lead backwards, and you assign them a value of 0, draw in your arrows to the rest of the nodes that are sensible, and then just follow the algorithm of summing the pathways together until you finally get to the end node. So that's example 2. Example 3. Find all paths from A to B while avoiding D. So similar to the previous question, except rather than making everything funnel through node D, we have to avoid node D at all costs. Now the way in which we do this is we say that node D is no longer a sensible pathway to go along. As a result, this path here and this path here are not sensible paths, or you're not permitted to travel along them. And as a consequence, node D itself is going to have a path count towards it as 0. Now filling in the rest of this network, I'm going to draw the arrows of edges we may travel across, or I should say arcs we may travel across. Since we don't travel along these two arcs over here, we also would not travel along these two arcs here. So we'd cross it out. But just to remove the clutter from the diagram, I'll remove them. Alright, now next step is we're going to fill in the rest of the values on this diagram. So this will be path count of 1 and 1. 1, 1, 1. So all the extremities have a path count equal to 1. Then filling in the inside nodes, path count of 2, path count of 3. and thus what we find are that there are 17 unique pathways we may travel to get from A to B while avoiding D. So in summary, what we had a look at in this lesson was a simple algorithm we can use to be able to deduce all of the paths that lead from a node and finish at a second node. Then we had a look at how we can alter this algorithm such that if we have constraints that say we must pass through a particular node, or if we have to avoid a particular node, how we deal with that.